There are certain things in physics 30 that we just have to understand, not remember, but understand. There's a lot more of that stuff in physics 30 than there was in physics 20 for sure. But one of those things is not what we're about to do here now. I mean, we want to understand it, right? Don't get me wrong. We want to understand what's going on, but what I'm about to show you has a lot of remembering to it. Now, that means that it's more like physics 20, right? In physics 20, we tend to be able to get away with remembering stuff. Okay, in physics 30, there's not as much of that. Okay, in this case, we can get away with remembering stuff. I'm going to show you a force versus time graph right now. Force on the y-axis, time on the x-axis. Doesn't matter what the shape of that force versus time graph is. I want you, every time you see that graph, every single time you see that graph, remember this. 3 words. Area equals impulse. You will, I promise you, on your unit test, see a force versus time graph. And when you do, I want you to automatically think 3 words, area equals impulse. You will, in all likelihood, on your exam in January, see a force versus time graph, and I want you to think 3 words, area equals impulse. You don't even have to know what the question is asking. I want you to automatically think area equals impulse, because the area between the x-axis and the line on the force versus time graph represents the impulse. Now, not all graphs are as straightforward as the one that you see up on the board here right now. Some of them aren't perfect straight lines. Some of them have a line that's partly above the x-axis and partly below the x-axis. But in all of those cases, we're still going to think area equals impulse. Let's take a look, though, at one that's a little bit more complicated. Force versus time graph, but this time our line is partly above the x-axis and partly below the x-axis. Still, area equals impulse. First 3 words that should always come to your mind here. But the area that's above the x-axis, between the line and the x-axis, will be a positive value. And the area that is below the x-axis and between the line will be a negative value. You want to find the total impulse here, the total area, you're going to add these up. And if the total area ends up being positive, you have a gain of momentum, a positive impulse. If it ends up being negative, then you have a loss of momentum, a negative impulse. So any area above the x-axis is positive, while any area below the x-axis would be negative. Now, there is something else that you sometimes need to do beyond area equals impulse. Not always. Sometimes the question just says, here's the graph, what's the impulse? And you're going to automatically go area equals impulse. But sometimes you need to find a change in velocity or a mass. If that's the case, that's fine. Doesn't matter what you're asked for. You're still going to first get area equals impulse. Always. First thing you're going to do, area equals impulse. But then you may also set that impulse, which is the area, right? Right, you've just found the impulse, it's the area, equal to m times delta v. If I've got the mass of an object experiencing this impulse, and I've just calculated the impulse by doing area equals impulse, then I can find the change in velocity of that object. Or, similarly, if I have delta v, and I just found the area, or the impulse, then I can find the mass of the object. You recognize this equation, right? This is half of our F times T is equal to M times delta V equation that appears on our data sheet. Conspicuously missing from that is the other half of that equation. Delta P is equal to F times delta T. I don't want you to ever try using that equation with this. It is technically valid. It is technically okay, but it will almost certainly lead you to a mistake. The reason being, that force that you see in that equation stands for average force. But on these graphs, the force is almost always changing. So what do we use? What value of force do we use when the force is always changing? Just don't even try. find the area, get the impulse, and then if necessary, set that area or set that impulse equal to m times delta v. Now, you also have to watch out for units. A lot of times the time seems to be given to us in milliseconds. Sometimes the force ends up being in kilonewtons or something else. So watch the units. When you calculate in the area, you know that you got to be in newtons, you got to be in seconds, the standard units. All right, I think you're good. Let's take a look at an example to kind of see how this plays out. The example that we're going to show you is actually in your textbook. If you don't have your textbook downloaded, that's okay. You can just look up here. Okay? But if you do want to download it, or if you haven't downloaded it already, you guys know that just to go into the About tab in Google Classroom and you'll find it there. This is chapter 9, page 462. It says a golfer hits a long drive, sending a 45.9 gram golf ball due east. Figure 9.22 shows an approximation of the net force as a function of time for the collision between the golf club and the golf ball. Look, I see my graph. I know right away that area equals impulse because that's just ingrained in me, or at least it is by the time your test comes around. There was nothing to think about there. There was nothing to think about there. We just remember that when we see this graph, whatever the shape of it is, we think area equals impulse. Now, I do want to pay attention to that ms, that milliseconds on the x-axis, because when I go to calculate that area, I want to make sure that I convert that. Listen, I don't even know what I'm being asked for yet, right? I didn't read question A or question B. Doesn't matter. Still thinking area equals impulse. All right. Now that I've written this down, become conscious of this, let's take a look at what I am being asked for. What's the impulse provided to the ball? Perfect. Okay, I know how to do that. I just solve for the area. So question A, I'm going to say the area or the impulse is equal to 1/2 base times height, because we got a triangle here. There's a rectangle, which would be base times height. A triangle is 1/2 base times height. Now, I remember a number of years ago when I did this question, I did way more work than I had to do. When I found the area of this, the first time I ever did this question, I broke this up into 2 right-angled triangles. I found the area of this one using 1/2 base times height. Found the area of this one using 1/2 base times height. What do you think I got? Same as I would have gotten if I had treated it as one object. Is there any reason why I need a right-angled triangle here? No. If I'm using sine, cos, or tan, I need a right-angled triangle. But the Pythagorean theorem, or 1/2 base times height, or Pythagorean theorem does. But 1/2 base times height doesn't require a right-angled triangle. So let's just do it as 1. I mean, I got the right answer when I did it the other way. I just did twice as much work as I had to do. My base here is what? 1? No? Yeah, it's 1. It's, well, almost 1. Look, we start at 0.1. You got to be really, really careful about that. You got to figure this is a multiple choice question, and you used 1.1 as your base. That option is going to be there. It's 1 because we start at 0.5, or sorry, at 0.1, I should say, and go to 1.1. So my base is 1, correct? My height is 5,000. Is anybody like sitting out there thinking like, I want to say something, but I'm kind of afraid that I'm wrong on something? There's something wrong here. There is something wrong with this. You guys had the right idea of the whole 0.1 thing and 1.1 thing, yeah? It's in milliseconds, right? We circle that in red to remind ourselves that it's in milliseconds and that we have to convert it. We can still use the 1, but if it's 1 millisecond, it's 1 times 10 to the minus 3 seconds. That make sense? Millisecond is 10 to the minus 3. If you're unsure of that conversion, check your data sheet. Okay, the last page of your data sheet, or sorry, the second page of your data sheet has in the middle of it prefixes used with SI units, it's called. And if you go down, you're going to find milli, it's 10 to the minus 3. All right, do the math here. On our calculators, we end up getting 2.5. The units would be either kilograms meters per second, or probably use Newton seconds. That makes most sense, I think, since we have newtons on the y-axis and seconds on the x-axis. There we go. There's the impulse. We had to think a little bit, right? Because we had to make sure that we used milliseconds, and we had to figure out which equation we used to find the area. But fundamentally, this was just area equals impulse every single time. Just do it. Question B. It's the velocity of the ball at the moment the golf club and ball separate. I'm going to trace through this graph. And I first, before I solve this question, want you to tell me where the club and the ball separate. Where does the club and the ball separate? Okay, just shout it out. Just say now or stop or something like that when I get to the point where the ball and the club separate from each other, all right? Some people are saying there. Okay, a few people said that. Yeah, you are. It's here. It's not up here. I knew that people were going to say this because that's where the force goes down, right? But if you think about this golf ball on the club, or sorry, on the tee, and then you hit it with a golf club, and you interpret this graph with that in the back of your mind, you can't have a force on the ball when the ball is not in contact with the club. We have a force right here. It's smaller than the force right here, but there's still a force. So the ball must be in contact with the club. If you were to look at a super slow motion video of a golf club hitting a golf ball, like super slow-mo, you'd probably find it on YouTube, I don't know. You would see that the golf ball compresses to a size about half its normal size when it's in contact with that club. And we learned a little bit about that last year, not in the context of golf ball, but last year you guys learned that as something like a spring or an elastic compresses, the force becomes bigger, right? F is equal to kx. Remember that Hooke's law? As the compression or stretching got bigger, the force got bigger. So here's what's happening. The golf club is hitting the ball. The ball is getting smaller and smaller and smaller and smaller and smaller, and the force becomes bigger and bigger and bigger and bigger. And then what happens? Well, the golf ball starts moving. The golf ball actually leaves the tee. So what happens here now? The force becomes smaller, 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 smaller as the golf ball goes back to its normal size and shape, but it's still in contact with the club, right? That's the idea of the, who's a golfer here? This would be your what? This would be your follow through, right? This would be your follow through. The reason you want to follow through, like think about this. The reason you want to follow through is to maintain contact of the club with the ball for a longer period of time, which is going to give you, if I increase the amount of time here, more impulse. And that if more impulse makes the ball go faster and makes the ball go farther, right? Typically, at least. You don't always want the ball to go faster and farther, but typically that's what you want to do, right? Same with a baseball bat, right? Or a hockey stick, right? If you're taking a slap shot. When you take a slap shot with a hockey stick, where do you hit it? Do you hit the ice, right? You hit the ice just before, right? I don't know if you necessarily think about that consciously, but the idea is to get the stick bent, before it makes contact with the puck, so that there ends up being more time of contact between the puck and the stick, which gives you more impulse, which makes the puck go faster. Okay. All right. If we know this entire graph represents the time that the golf ball is in contact with the club for, how do we find this velocity of the ball when they separate? Separates down here. Okay, separates down here. So we're going to use that entire impulse that we just found, and we're going to set that equal to m times delta v. 2.5 is equal to 0.0459. Got to convert that grams to kilograms. Again, you don't remember the conversion factor? Check your data sheet. 1,000 grams in a kilogram. Solve for delta V there. I think it was 55 or 54, something like that. 2.5 divided by 0.04, 54 point. Okay, so we're going to say 54.5 meters per second. Now, what am I looking for? Not the change in velocity. I'm looking for the final velocity. But if the initial velocity is 0, and it is because the golf ball is sitting on the tee, then what's the final velocity? Well, it's the same as whatever the golf ball changed by, right? If it changed by 54, then the final velocity is going to be 54. Now, if the initial velocity wasn't 0, like you were talking about baseball, right? If the baseball is coming towards you with an initial velocity, then the final velocity would not be the same as the change in velocity, right? It would be different, but you'd have to be given an initial velocity in that case if that was the situation, right? What equation did I not use with this? What equation will I never use with one of these problems? Force times time, because what force do I use? Like it's changing the whole time. Easier just to do it the way we did. Okay, I want you to take a look at a couple questions that are also on page 462 from your textbook. Whether you download that chapter of the textbook or whether you just look up here, it doesn't matter. Whatever's easier for you. I'll give you some time to work on these in class here now. All right, I want to look at number 1 here. It says, draw a graph of the net force as a function of time for the 0.650 kilogram basketball. During the first 0.15 seconds, the force increases linearly, so in a straight line, from 0 to 22. And during the next 0.25, it decreases linearly to 0. So here's my graph. I go from, 0 to 22 during the first 0.15 seconds. So let's make this 22 newtons, and let's make this 0.15 seconds. And then I decrease during the next 0.25 down to 0. So it's going to look like this. Now, I know there was at least a couple people that made this mistake in this class. There was in the other class as well. I'm not surprised. Okay? It's an easy mistake to make. This is not 0.25. Rather, this is 0.4 because it says during the next 0.25 seconds. So 0.4. Now, we automatically think area equals impulse. So to find the area of this, to find the impulse of this, we're going to say it's 1/2 base times height because it's a triangle. 1/2 of 0.40 times the height of 22 gives me, should be 4.4 Newton seconds. And then I want to find the speed of the ball when it leaves the shooter's hands. So let's say delta P is equal to, what equation would I use? M times, not M times V, M times delta V, okay? We don't ever want to say M times V because then we're going to, in this case, it would have worked out. Right? But sometimes when VI is not 0, you're going to mess up on that. M times delta V. We're going to solve for delta V here. Delta P over M. So it ends up being equal to 4.4 divided by the mass here of, what was it, 0.650. And that should work out to be 6.8 meters per second. Now that's the change in velocity. We're actually looking for the final velocity, but before it left his hands, it was 0 meters per second. It started at rest. So the change in velocity will be the same as VF. Good. How many people are finished question number 2 now? Okay, let's take a look at that. Number 2 says a soccer player heads the ball with an average force of 21 newtons west for 0.12 seconds. You can see the graph right here, although it's pretty small. One thing you got to watch out for here is this whole west thing. The way that they have it drawn is that the line is above the x-axis. If that's the case, then they've effectively made west positive, right? Usually you make west negative. It's okay to make west positive as long as you know that that's what you're doing. Now, I don't know what I'm being asked for. I know that I'm going to think area equals impulse. And sure enough, in question B, it asks me to find the impulse. So let's say area equals impulse, or we're going to say base times height because it's a rectangle. The base here is 0.12 seconds, and the height here is 21 newtons. And that adds up or multiplies together to give me, I think it was 2.52 actually, I think, wasn't it? Which rounds to 2.5 Newton seconds. I get a positive value for that. So what's the direction? West, because we define west as positive. I don't need to write the word west in as long as I define west as positive. Then it's all good. The impulse changes the velocity from 4 east to 4 west. Now, this is going to be a little bit confusing. What's the mass of the ball? We know that delta P is equal to m times delta V. It's also equal to F times T, but we don't want to use that because the force... Actually, this is the one question where you could get away with using F times T, right? How come? Because the force is actually constant, isn't it? You know what, though? Just don't. You could do it and it would work. But if you start doing it, then you're going to forget and do it some other time when it's not going to work for you. So just avoid using F times T. All right, we've got delta P is 2.52. M is what we're looking for. Delta V, be careful with this. Final minus initial. The final is 2 to the west. It's 2 positive or negative? Positive, good, because we defined west as positive. Subtract negative 4. So this is unusual the way we've set this up, but we've done it this way because of the graph. The velocity is to the west, the force, sorry, is to the west, and we've drawn it above the x-axis. So 2.52 divided by, what would that be, 6, gives me an answer of 0.42 kilograms.